Morning, everybody. Today we're going to talk about chapter 4 in our book, which is about solutions and a special type of solution, which is a colloid. But both of those are homogeneous mixtures where you take one material and it is dissolved into another material. So that's what the topics are going to be about. It's going to describe the various conditions of solutions, why things go into solution versus other things don't go into solution. And it's also going to do some calculations involving materials that are in solution, figuring out how much is actually present in that case. So to first off describe what we're talking about, solutions are a homogeneous mixture of two or more substances, and because they are homogeneous mixtures, they're uniform in distribution, the particles never settle out. They're also uniform throughout in their composition. So the beginning material, the material at the top of a solution, the material in the center of a solution, the material at the end of a solution are all the same and uniform. So if you had a uniform solution, no matter where you sample from, over here, down here, over here, it's all the same material throughout, and you don't get any differences in sampling no matter where you search from. So you get the same material regardless of where you are in location, regardless of how old or how it's there. Things never settle out, they never change for those types of solutions. Another property of solutions is that they're transparent because the particles are uniformly distributed, they don't settle. Light passes through a solution without any problem, and you don't see, and you can see through it. So a clear solution is a little bit different than a colorless solution. You can see these are all different solutions of different colors, but you can see that light goes through them, and you can see from one side to the other. Air is also a colorless solution that's clear, but other materials such as clear liquids or liquids that you can see through, like this blue liquid right here, this is a solution that has a color, but you can still see the light from one side. You could put your hand on the other side, you'd see your fingers on it. And that's a property that solutions have. That's an indication that it's a homogeneous solution, that light is able to pass through it, the particles aren't going to settle out. And if you compare to that something like milk or something like fog, where you can't see the other side because the light is blocked and scattered, that's a different type of material that we'd be talking about. So when we're working with solutions, there's two different terms that we're going to be using. So solution is the mixture itself, and a solution is made of two different things. It's made of the solvent, which is the most abundant kind of bulk compound that everything's dissolved in. So if we're working with a solution of like salt water, water would be the solvent in that case. Water is what everything's dissolved into. If we're working with like a juice or a tea, also the water would be the abundant compound, the solvent in that case. But we could also be talking about something like air. Air is a mixture of various gases, and it's oxygen dissolved essentially in nitrogen. So nitrogen gas would be the solvent in that particular example. The other material that's in a solution is the thing that you've dissolved, the solute. So the solute is the thing that you did dissolve in the solution. So solute is the material that's dissolved. So if we're working with salt water, it would be the salt. If we're working with oxygen and air, it would be the oxygen dissolved in the nitrogen. Nitrogen would be the solvent, oxygen would be the solute. And there can be more than one material in that solvent, more than one solute. So just like with our example of the air, right? Oxygen is one of the solutes in air. Other solutes that are in air are carbon dioxide, argon gas, hydrogen gas, other gases dissolved in that air. For a drink that you may be drinking, a really simple drink may have some type of flavor molecule and some sugar. So water with some flavoring is the solvent, some flavor molecules are the solute, and some sugar is the other solute. So multiple compounds there. And when we're talking about solutions, usually people think about solutions that are liquids, but solutions can be gases as well. Just like the air is a solution, it's a gas. You can also have solid solutions. And so the solutions can be solids, liquid, gases. The solvents can be solids or liquids or gases. And the solvents can be solids, liquids, or gases. So all the different combinations exist for a solution. So we can see here all the different examples and all the different combinations that you can have. Water that is in a solid state. You can, or water that's a solvent with solid state solutes. You could also have water as a solvent with solution, with a liquid solute or a gas solute. So water is our liquid here, and we got three different types of water, and they've got either liquid state for all three of those. But the solvent for all these is water. But depending on what the solvent that we had in it, we could have a solute added to it. We could have salt water. We could have a gaseous solute added to it. We'd still have water, but it's water with a gas dissolved in it. We could also have water with a liquid dissolved in it. So water as a solvent, in this case, is a liquid, but we could have all sorts of different solutes added to it, solids, liquids, or gases added as solutes. And there's other types of solvents as well and other types of solutions. Air is another solution or is another gas type solution. And air itself is nitrogen gas with other gases dissolved in it. And that's one example of a gas with another solution with gas solvents. But also, if you're breathing oxygen through a mask and you need to add a little bit of humidity to it because oxygen's very dry otherwise, you could have oxygen gas with a little bit of water added to it. So this is a gas, this is a solvent that's a gas, but it has a water or a liquid solute. So this is a gas solvent with a liquid solute to produce a gas solution. Solutions don't have to be liquids or gases though, they can also be solids. And if you have anything around made of 14 karat gold or any type of gold, gold is also a solution. Gold is a solution of gold, the element here, which is solid, but they add different amounts of other materials to gold to make it a little bit more workable. Gold is very, very soft and it wouldn't stay in its shape very well, so they add small amounts of copper, which is a very hard metal element, and that makes the gold a little bit more likely to keep its shape. Otherwise, it would bend out of shape anytime you hit it with anything. So gold is a solution as well, and it's a solution of solid gold mixed with solid copper. So two solids dissolved together, solid copper is the solute dissolved in solid gold, makes a solution that is a solid, and we call that 14 karat gold, and various levels of gold carats tell you how much gold is in it versus how much copper. But that's a solution as well. So solutions can be liquids, liquids mixed with liquids, liquids mixed with solids, liquids mixed with gases. Solutions can also be gases, gases mixed with other gases, gases mixed with liquids, gases mixed with solids. And it can also be a solid solution, solid solutions, solids mixed with solids, solid solvents mixed with liquid solvents, solids solvents mixed with gaseous solutes. So you can get all sorts of different combinations of solvents, solutes, and solutes in any case, in any state, and you'll still get a solution in the end. Colloids are another type of solution, and they're like solutions, but they're a little bit different. So colloids are very similar to solutions, so we're going to mention them here, just kind of to mention what they are. Since solids are very similar to solutions, but they have one key difference, and that's that colloids will scatter light. So solutions are colloids. Colloids are homogeneous mixtures, just like a solution are. They don't settle down like a solution will either, so neither will solutions or colloids settle. They'll stay in solution indefinitely. The particles don't fall out of solution. If they did, that would be a heterogeneous mixture, and you wouldn't have a colloid. You wouldn't have a solution. So if you take a bunch of sand or a bunch of dirt and put it in water, and you can mix it around a lot and you get that nice brownish liquid, but eventually all the dirt falls out of solution, all the rocks fall out of solution. That's a heterogeneous mixture. Versus if you take a bunch of sand, salt or sugar and you dissolve that in solution, that goes up into solution and it never leaves because that's a homogeneous mixture and it doesn't settle. So neither will solid colloids, neither will solutions. Those won't settle. The mixture, the particles aren't going to fall out of solution. But the key difference between a solution and a colloid is that solutions don't scatter or reflect light. You don't see the beam. If you were to take a cup of tea or something with a light kind of solution and you were to look through, the light would go right through that solution. Take some juice or something like a light lemon juice mixture, you can get the light to go right through that. No scattering of light. Versus something more like a colloid, more like something like a glass of milk, or a really foggy room. If you've been using a shower and there's all the fog afterwards, all the steam, you can see the particles almost in the air. That is a colloid. Colloid particles are really, really big compared to the particles in a solution, and even though they don't settle, they do scatter light. And you can see that with this sample over here. If we shot a beam of light from a flashlight at these little jars. The middle jar is a solution right here, so there's no scattering of light. But these other two right here on the sides are colloids, and you can see the beam going through the jar. And it just goes through, and you can actually see the line from the beam from that. And this is just like if you're driving at night in the fog and you turn on your headlights or you turn on a flashlight and you can see the beam from the flashlight, or if you're in a smoky area, you can see the beam from the flashlight because you're in a colloid in that case. It's a colloid, which is a air, so it's a gas, but it has particles of solid smoke or particles of liquid water in it suspended, and those particles scatter light, and you're in a colloid system. Colloids are very similar to solutions, so they use the same kind of phrases of a solvent and a solute, except rather than calling it a solvent, they call it the dispersing medium. Instead of calling it a solute, they call it the dispersed phase, but it's essentially the same conditions as a solution, where you have a solvent, the thing that's dissolved, and the solute, the thing it's a solvent is where it's dissolved into, solute is the thing you're dissolving. And these are just some different examples of colloids that you may have seen. So colloids can be in any, just like a solution, can be in any phase. You can have solids, liquids, or gases. So the dispersing medium versus the dispersed phase. So this is the equivalent of the solvent. So our solvent equivalent, we can have a gas type solvent. So we can have a gas solvent with a liquid solute that we've dissolved in it. And that's things like fog. So if you're driving around on a foggy night or a foggy morning, the air has little drops of water in it. And that's an aerosol type system. It's got drops of water dissolved in a large gas. And just like we had said before, solvents and colloids scatter light. You can see the beam when you go through it. And if you're driving with the fog and you turn on your lights, you'll see that beam. And that's why it's hard to see, because the light gets scattered by the fog. Other gases that can have things dissolved in them are things like smoke, which is, rather than being a liquid like the fog water, is smoke particles, which are small solids, but same effect, you get that scattering of light. Other types of things that can be solvents, though, you may have experienced things like whipped cream or shaving cream. That's a foam. And foams are when you take gases and you dissolve a gas in a liquid. So you have liquid cream, cream's a liquid, but you add gas to it and you dissolve that gas in the liquid and you produce a foam. You can also make things like emulsions like milk. Milk is actually a solvent, a colloid system as well. It's little drops of fat, which is a liquid, dissolved in the rest of the milk, which is also a liquid, and that produces a mixture that scatters light. That's why milk, even though it's a liquid, it scatters the light. It has that kind of color and that shape and that shine to it, and you can't see the other side of the milk because milk is scattering light. You can also have solids dissolved in liquids, and that's what paints are, that's what inks are, that's what jellos are. You take a solid, dissolve it in a liquid, so a liquid solvent, and then you have a liquid with a solid in it. You can also have solid foams, which are solids with gases dissolved in it, and that's like if you have a marshmallow or if you have some rocks that are kind of foamy, kind of shaped with holes in them, you dissolved a gas in a solid, and that's what a marshmallow is. You can dissolve a liquid in a solid for things like cheeses and butters, or you can dissolve solids in solids, and that's where you get gases, glasses, and metals. So just like with the solutions, colloids can be any type of solvent state, solid, liquid, or gas, dispersed into any other solid, liquid, or gas state. And then you can see here just examples, colloids and solutions, similar behaviors for both of those, how you have a solid and a liquid or a solid and a gas, but colloids and solutions are very, very similar to each other in terms of properties. The only difference is that solvents and solutions do not scatter light, colloids do. So that's the key difference between those. Otherwise, they're very, very, very similar. So when we're talking about materials being dissolved or not dissolved and making solutions, a solution is when you have something dissolved in something else. So if something doesn't dissolve in the solvent, you can't make a solution. So if you try to make a solution of sand and water, sand is not soluble in water. So sand doesn't dissolve in water. That means that we can't make a solution of sand and water because they won't mix together, they won't dissolve. So solubility is whether or not something dissolves in something else. So sand is not soluble in water, but sugar is. So if I take some sugar or if I take some salt and I add that to water, that is soluble. That does go into solution. So if you're talking about solubility, you're talking about does something go into solution or not? And sometimes if you're talking about two liquids dissolving in each other, sometimes they'll use the term immiscible instead. So an insoluble, so you could say that sand is insoluble in water. You could also say that water is insoluble in oil, or oil is insoluble in water. If you take oil and water and you try to mix them together, you'll see they don't dissolve in each other, so they're insoluble. But sometimes they'll say instead that they're immiscible. Two liquids do not dissolve in each other. Two liquids are insoluble. Sometimes you'll see this word immiscible instead. But that's only when we're describing liquids dissolved in other liquids. The other phrases that happen, or the other thing you might notice though, is that usually there's a limit to solubility. So sugar is soluble in water, as you can see here, and you could take about 1 gram of sugar and you could put that into the water, no problem. And you would have a nice homogeneous mixture of sugar plus water, and you would have this nice mixture here, homogeneous mixture, a solution of solid sugar dissolved in liquid water. But and you could add another drop of sugar, you could add another gram of sugar, and you could keep adding sugar, but eventually you're going to run out of water molecules to dissolve that sugar. So if you took a ton of sugar, like 300 grams, that's a good amount, that's like a whole bag, and you dissolve that into a cup of water, a good amount of it will go into solution. But eventually the sugar is going to stop dissolving just because there's not enough room in the water for all that sugar to go. And then you're going to have a whole bunch of sugar left over on the bottom. And now you still have a sugar water solution, but it's not homogeneous, it's a heterogeneous solution because there's all this extra sugar at the bottom that didn't dissolve. There's a limit to how much sugar can be dissolved in water, and most materials have a solubility limit. But that limit is based on a couple different things. It's often based on the temperature, and it's based on the volume. So if you increase the amount of water, you could put some of the sugar into solution because there'd be more water. Maybe you raise the temperature, some of the solution goes into, sugar goes into solution as well. So the limits to a soluble substance can be overcome by either changing the amount of solvent volume for the solute, or by changing the temperature of the solvent. With liquids, this isn't as big a deal. So with liquids, as long as two liquids are soluble, they'll remain soluble no matter how much liquid you add. So you could take a big cup of water and you could add a few drops of alcohol to it. You'd have a nice homogeneous mixture like you did before. Or you could take a whole bottle of alcohol and add it to a solution, and it would still be homogeneous. Two liquids that are solvents for each other, or two liquids that are soluble in each other, will be soluble no matter how much you add. Two liquids, same thing for two gases. Two gases will be soluble no matter how much you add. Generally two solids also. So if both the solvent and the solute are in the same state, so if they're both liquids or both solids or both gases, then you can add as much of the solute as you would like. You'll never overcome the solvent. But if they're different states, then you may have a problem where one will be eventually run out of room for the other. So you'll get to the point where if you had a solid dissolved in a liquid or a gas dissolved in a liquid, you may get to the point where it no longer dissolved, you've reached the solubility limit, and then you can't add any more of that substance, even though it is soluble. So there is a limit to how much a soluble material can go into a solution if the solution and the solvent are different states of matter. And this is just showing here that temperature does make a pretty big effect. So most materials, especially when you're working with a solvent that's got a solubility limit, as you increase the temperature, generally that makes the amount of material you can dissolve increase. But at some point, you're going to get to the point where you can't add any more solvent, and that's where you get a saturated solution. That's the maximum amount of solute that can be dissolved in a solvent, And once you reach saturation, you can't go anymore. So if you think about like a sponge that you have on the side, if it picks up some water, you can add some water to that sponge, and then you can add some more water to that sponge. But eventually you get to the point where you can't add any more water. And once you get to that point, if you add water, nothing happens. It doesn't go into the sponge, it just kind of spills out. That sponge is saturated with water. Just like here, these materials, when you've added enough material, they become saturated and you can't add any more. So for our example here with sugar, at 20 degrees, we can add about 200 grams of sugar to 100 grams of water, and after that, we can't add anymore. So if we try to add 250 grams of sugar and the temperature is only 20 degrees, we can't add any more than 20 grams, and if we added 250 grams, then 200 grams would go into solution, and the other 50 grams would sink down to the bottom, and we would have a saturated solution of sugar. No more sugar can go in. But if we were to raise the temperature to 60 degrees, now we can put in 300 grams of sugar. So if we wanted to dissolve 250 grams of sugar, we can't do that at 20 degrees, but we can do that at 60 degrees because the amount of the sugar's solubility increases with temperature, and it changes as you increase the temperature. Different materials respond differently. So sugar, it's pretty big impact. This KNO3 at 100 degrees, you can put 240 grams of KNO3, but down at 0 degrees, you can only put 10 grams of KNO3. So depending on what temperature you're at, and if you're at 60, then you could do about 100. So depending on what temperature you're at, the solubility will change. Most of the time, solubility increases with temperature, but every once in a while, you'll see it doesn't. So gases are the key exception to this. Generally, solubility of solids and liquids increases with temperature, but the solubility of gases decreases. And you can see that here with the SO2. SO2, at 0 degrees, you could put about 30 grams of SO2. At 40 degrees, you could put about 2 grams or 0 grams, and above 45 degrees, you really can't put any SO2 gas into solution. And that means that gases don't dissolve well at high temperature. They only dissolve in liquids at low temperature. And if you think about your bottles of soda in the fridge, that makes sense. If you take a bottle of soda that's in the refrigerator and you open it up outside, as it warms up, you'll note, and you pour it into a glass, you'll notice the bubbles start appearing on the side of the glass as the solution warms up. As the solution warms up, the gases that are dissolved in the liquid leave the liquid, and they either float out of the liquid to the air, or they float out of the liquid and stick to the side of the glass. But originally that glass had very few bubbles, but if you watch over time, more and more bubbles increase. And if you want to try an experiment at home, you can take 2 glasses that are the same, pour a solution, like a soda solution, into one glass, leave the glass on the counter, put the other glass in the fridge, and then come back in a few hours and see how many bubbles are on the side of each glass. And you'll see the bubbles on the glass of the fridge will have less bubbles than the glass outside the fridge. And that's because in the refrigerator, you're down at this level here, you have a much higher solubility than you do when you're outside the fridge, which is over here. So the solubility is lower outside of the refrigerator at warmer temperature, means that more of the gas is going to escape than it was in the fridge. So when you have a drink and you want to keep the bubbles in it, that's why we store stuff in the refrigerator for bubbly drinks. Gases also have higher solubility if they're stored under pressure. So taking the lid off is going to make that pressure lower, and that means that more of the bubbles will escape. So keeping the lid on, that keeps the pressure in longer. And that's why every time you open that lid, you hear that hiss of gas escaping, because when you open the lid, you let some of the pressure release, and that releases some of the gas from the solution. So solubility is affected by temperature. Generally, solids and liquids are more soluble as the temperature goes up. Other things like gases, temperature makes as the temperature goes up, solubility goes down. But for any of these types of charts, it's usually a chart of temperature. Temperature is, in this case, down here on this axis, and on this axis right here is the solubility, how many grams of something you can dissolve. And so if we wanted to read this, at 60 degrees, how much KBr we can dissolve, we go to the 60-degree temperature line. We find that number, we find KBr, and then we go across, and we can see that at 60 degrees C, we can dissolve 80 grams of KBr in 100 grams of water for this particular chart. That's how you would read that chart. And you could do that for any of these. If you wanted to figure out at 70 degrees what's the most soluble material, well, it turns out at 70 degrees, the highest solubility is the KNO3, followed by the NABr, followed by the KBr, and then glycine and KCl are pretty much identical at that point. They're kind of here. So they're very similar, but they're the lowest solubility. KNO3 would be the highest solubility, and then if you go up really high, sugar is even higher than all of those. So sugar is very, very soluble in water. These other materials are a little bit less soluble in water. So when we try to look at a solution and try to figure out whether something will dissolve in another material, whether a solvent will dissolve a particular solute, there's a few base rules that can help you figure that out. And the first rule that matters with that is that like things dissolve like things, or materials dissolve stuff that's like them. So if you were to look at a series of different solvent and solute pairs and try to figure out what makes it would go into solution and what wouldn't, generally things that will dissolve things that are similar to them. So if you have an ionic solute or an ionic solid, it'll dissolve well in an ionic liquid or a polar solute or a polar solvent. So polar materials dissolve polar materials pretty well, and nonpolar materials dissolve better in nonpolar solvents. So nonpolar solutes dissolve in nonpolar solvents, polar solutes dissolve in polar solvents, and ionic behave very similar to the polar in that they prefer polar materials as well. And the reason for that is because when you're dissolving something, all the material you're trying to dissolve already has all of these different interactions going on in it. So for example, down here, the salt molecule is interacting with all the different components in the salt. So the sodiums with a positive charge are interacting with all the different chlorines with a minus charge that are around them. And those sodiums are held in place through all these different interactions. So the sodium here is held in place by 3 different chlorine atoms, and the sodium over here has 2 chlorine atoms holding it in place. So those sodium atoms are held in place by all these different chlorine atoms that are attracted to it. And the same thing happens with the chlorines. The chlorines are surrounded by a network of sodiums, and that means that all the sodiums and all the chlorines are holding on to each other pretty tightly. And that's why the salt molecule stays together, why this compound NaCl stays together as a compound of Na and Cl atoms. And they stick around with each other. Meanwhile, the water is doing something similar. The water molecules, water being a polar molecule, hydrogens are a little positive, and the oxygen side is a little negative. So the negative side of the oxygen is interacting with the positive sides of the hydrogens, and it produces this little network of materials. And you can see the same thing over here, this positive hydrogen interacting with the negative oxygen, and this negative oxygen interacting with these positive hydrogens. So this interaction is pretty strong in the solvent, in the water, and it's pretty strong in the solute down here in the salt. So to overcome this interaction and get something to go into solution, we need to get the solvent interactions, the interactions between the different water molecules. We have to overcome those interactions between the water molecules. We have to overcome these interactions between the solid and the solute. And if you can overcome both of those, and you can form bonds and interactions between the solvent, the water, and the NaCl, the solute, that are stronger than the interactions to the other water molecules and the interactions to the other salt molecules, then that salt will go into solution. And we can see that here. Now we've overcome some of those interactions, and now the positive side of the NaCl is interacting with the water over here. The positive NaCl is interacting with the negative oxygen. The negative Cl is interacting with the positive hydrogens. These atoms are able to interact with each other because now the interactions between the solvent, the water, and the solute are much more stable compared to any interactions that was holding the water molecules together. These salt molecules had to get between the water molecules, so the interaction between solvent and solute has to be stronger than the interaction between the water molecules that's already there. And this is just showing some different examples. So we already talked about ionic solids like NaCl down here interact very well and dissolve very well in polar solvents. And to do that, what happens to happen is that the interaction between all the different ionic components, all the different ionic components in that molecule have to be overcome. So this positive ion right here is surrounded by a whole bunch of negative ions around it. And if we can overcome that interaction between those positive ions and those negative ions and put it into solution, this ionic solid will dissolve. And we do that because the water molecule has all of these negative regions around the oxygen, and those negative regions around the oxygen can surround the positive ion, just like how the positive ion in the salt was surrounded by all these negative ions in the salt molecule. So just like how in the salt, in the solid, the ion was surrounded by a bunch of negatives, and that was able to stabilize the molecule. In solution, that same ion is surrounded by a lot of negatives, and it's able to go into solution as well. And the same thing happens with the positive ion, with the negative ion. So the negative ion here is surrounded by a bunch of positive ions in the ionic solid state, in the solute state. But what happens is when it gets dissolved in solution, it's now surrounded by all the positive components of the water. So the solid ionic compound, which had the ionic solute, which was surrounded by negative ions before, is now surrounded by negative ions, and the negative component of the ionic solute is surrounded by positive solvent molecules. And that means that everything's interacting the same way, and it goes into solution. These are sometimes called hydrated ions. Hydrated ions are ions that are surrounded by water molecules, just like this positive ion here is surrounded by a bunch of water molecules in such a way that all the negatives are pointed toward it. And this negative ion here is surrounded by water molecules in such a way that all the positive sides of the water are pointed toward it. Those are both hydrated ions, or ions surrounded by water molecules. And this is going to happen for every single ion in this solute right here. So slowly, as the sample dissolves, more and more of the ions interact with water, and they go out into solution until the entire solid or the entire solute has been dissolved. And this can happen with both ionic compounds, but it can also happen with polar molecules. Water is a polar molecule, and water will dissolve other polar molecules as a solvent. And you can see that here. Normally, the positive component of this ion or this dipole is interacting with the negative components. So our positives are over here, and our negative components are interacting with our positives. So there's a negative here interacting, a negative here interacting, a negative here interacting with the positives. So positives and negatives are interacting in the solute state, but as that solute gets exposed to water, the water molecules also interact so that the negative is interacting with the positive and the negative is interacting with the positive. So negatives and positives are still going to interact. It's just now the negative and positives of the solute and the water interacting with each other. And as that happens, the solute starts to become dissolved and surrounded by water molecules. And then slowly, the solid dissolves. The solute dissolves by the water molecules surrounding the different components of that, so that the positive component is interacting with the negative component, the positive component is interacting with the negative component, the positive component is interacting with the negative component. And because water is a dipole, it has a positive and a negative component to interact with the solute, which is also a polar molecule. And that's different if you have a molecule that's nonpolar. So here now, this molecule doesn't have a positive or a negative component. This molecule doesn't have a positive or a negative component. And because there is no positive side to interact with the negative part of the water, it doesn't go into solution. Because there is no negative side to interact with the positive side of the water, it doesn't go into solution. It would rather hang out on its own with all the other molecules that look like it. So like things are remaining with like things. This like solvent is staying by itself where the positive and negative of the water can interact. And the solute is staying where it is so that the non-negative and the non-positive, non-charged region of this solute can interact with itself and it doesn't go into solution because there's no positive or no negative regions on that molecule to interact with the water. And that's really different than the other examples where it does, right? There's a positive ion here, and it's going to interact with the negative parts of the water. There's a negative ion over here, it's going to interact with all the positive parts of the water. This thing over here, negative interacting with positive, negative interacting with positive, negative interacting with positive. And then on the other side, positive interacting with negative, positive interacting with negative. Because the molecules have a positive and a negative component, the water molecules are able to dissolve them. So solids and solutes that are ionic, solutes that are polar, are both soluble in polar molecules like water or polar solvents like water. So anytime your solvent and your solute are similar, they're same compounds, they're both ionic solutes, they're both polar solvents. Anytime polar molecules or ionic molecules, they'll dissolve in polar or ionic solvents, and nonpolar components or nonpolar solutes dissolve better in nonpolar solvents. And that leads to this thing though, what if you want to dissolve a polar molecule in a nonpolar solution? Or if you want to dissolve a nonpolar molecule in a polar solution? Water is polar, but things like grease and oil are not. So if you get grease or oil on your clothes and you want to pick it up, how do we do that? Well, we can do that by using some special molecules that have both a polar part and a nonpolar part. And since we have molecules that are both polar and nonpolar, they can dissolve both of the polar and nonpolar parts of any molecule that we're trying to dissolve. So soaps are special molecules. They contain a polar component and a nonpolar component. The polar component of the soap is right here, has a charge group, a C, an O, and a minus charge, and then also a positive charge. Or this one over here, S with a bunch of O's. This is a very polar region of a molecule right here. And this section over here of the soap or the detergent is going to interact with water. And that's going to make this soap soluble in water. But soaps also have a part that's non-interacting with water. It has this very non-polar region, just a bunch of carbons and hydrogens, nothing polar about this section over here. And because this section is non-polar, it's going to interact with other non-polar parts of the other molecules like grease. So if you had some grease or some oil, and you wanted to dissolve it in water, you would use a detergent or a soap, which would have the non-polar region that interacts with the molecule and a polar region that interacts with the molecule in the solvent of water. So this oil is going to hang out over here with this section, and then the water is going to hang out in this section here, and that allows you to dissolve your oil or your greases in water by adding soap. And you can see some examples of that happening here. We have this molecule here that's very, has some grease or oil in it. And normally grease or oil, being a very non-polar molecule, is not going to go into solution at all of water because water is polar, grease or oils are non-polar, and it's not going to be dissolved. But if you take that same grease and you add some detergent to it, the grease will interact with the detergent in the non-polar region. So this is the non-polar region of the oil and the non-polar region of the detergent, and they'll all interact together and they'll dissolve. But because that non-polar region is also attached to a polar molecule at the top, that part can interact with the water out here, and now the water is going to interact with the outer part of the molecule, the part that's polar, and the grease is going to interact with the nonpolar part of the detergent, and this detergent forms a shell around the grease, and then the outside of the detergent is polar, and that goes into solution. So you have these little grease balls surrounded by these polar regions, and that goes into solution. So you're able to pull the grease or oils out of your clothes by using things like detergents or soaps. Other things that we have to deal with when we dissolve things is that even for things that do dissolve really well, and things that dissolve and go into solution really well, they may dissolve even though they're extremely soluble. It may still happen at a very low rate. And that doesn't mean that it's insoluble, it just means that it happens slowly. But there are certain things you can do to make it faster. So if you think about dissolving things, one of the key things that affects the rate at which something dissolves is the surface area. So if you look at these two examples here, this sample has a very large surface area for what we're dissolving. If we were instead to smash that up into areas with lots more surfaces, then now we have all more surfaces. We have this whole region over here that's accessible, this whole region that's over here that's now accessible, these other spots. So there's more spots for the water to come in and dissolve stuff, because solutions only dissolve solvents, only dissolve solutes at the surface. So the more surface there is, the more regions there are for that reaction to occur, and the more frequently that reaction occurs, the faster it goes into solution. So breaking up a large molecule will cause a molecule to go into solution faster. So if you think about sugar cubes versus powdered sugar versus grain sugar, if you try to dissolve a sugar cube in solution, it doesn't happen very quickly. But if you were to smash up that sugar cube into bits of sugar, it would dissolve, it would go into solution much faster. That's one thing we can do. Another thing that we can do to raise the rate of something going into solution is to bring the temperature up. Generally, temperature makes rates go faster for reactions. So just like with our sugar, if you want to dissolve a molecule of sugar and you're trying to dissolve a lot and it's not going into solution very well, just heat it and it goes into solution much faster. So heating up the solution makes it go into solution faster. And the final thing you can do to make the molecule go into solution faster and dissolve that solute and that solvent any faster is by stirring or mixing around the solution. So normally if we were trying to dissolve this big block of sugar right here, then it would only interact at the surface. And then those surface molecules get picked up and they go into a solution, but they're not going to get very far. But if you were to stir the molecule and stir the solution, that would allow these molecules to move out of the way so that new molecules of solvent can come in and grab the solute and go into solution as well. So you're just causing things to move faster, and you're preventing any local saturations from occurring by allowing that surface area to get exposed to more and more solvent. And that means that eventually that solute will go into solution, and it'll happen much faster when you increase the rate of dissolving by causing the mixture to be stirred. When you dissolve something, another interesting factor that can happen is that materials can dissolve in solution, so solute will dissolve in a solvent, and sometimes when that happens, the sample releases energy, and it usually releases that energy in the form of heat. Sometimes it releases energy, sometimes it requires energy. So if you look at a sample and you dissolve it in water, so an example of this would be like dissolving sodium hydroxide in water. If you started mixing that up, you would start to notice it actually becomes rather warm and it releases heat. So some samples and some solutions, when you dissolve them in water or any compounds, that solution process actually releases energy, and it releases that energy in the form of heat. And generally, since things dissolve faster and go into solution faster when they get warm, as this thing warms up, more of it becomes soluble, it dissolves faster, releases even more energy, and it starts to get really, really warm really quickly. And that's a way you can make a chemical heat pack if you had a molecule that you knew released energy or released heat when it dissolves. Other things you can do is that you can also look at samples that are warm and absorbing energy. Some samples absorb energy when they become warm and when they become dissolved. And as they absorb that energy, they absorb energy and they go into solution and they get colder. So this sample here is going to be absorbing energy, and the energy is going to cause the sample to become cooler as you add more and more of the solvent. So regardless of how we dissolve, if something goes into solution or not, we do want to be able to record what the actual amount of material that is dissolved in that particular solvent is. And one way to do that is to record it in terms of molarity. Molarity is abbreviated as capital M, and that's the number of moles of a solute that is dissolved in a liter of solution. So if you have a 1 mole of solute dissolved in 1 liter of solution, that would be 1 molar or 1 m in concentration. So to figure out the molarity of something, it's just the number of moles divided by the volume of the solution, and that's going to be moles per liter. So if we had a sample that had 1.5 moles of NaCl and it was in a solution that was a 3 liter in volume, then we could figure out the concentration of that solution. 1.5 moles divided by 3 liters is just the number of moles divided by the volume. And that means that this particular solution has a concentration of 0.5 moles per liter, or 0.5 molar, or a 0.5 molarity solution, 0.5 m. So that's an example of ways to report the concentration of a solution. And we've got a few different examples of that. So here's another example here. We're looking at a sample that's 250 milliliters of solution, and in that 250 milliliters is 0.134 moles of a particular solute. So again, remember that we have to convert, though, because it's moles per liter, not moles per milliliter, we're going to have to convert milliliters into liters, and we can do that, and as long as our milliliters up here cancels with our milliliters down here, then we know that milliliters and milliliters cancel. The only unit that doesn't cancel is liters. That's our final volume there. So we know 1 liter contains 1,000 milliliters. So 250 divided by 1,000 means that we have 0.250 liters. And then we can just plug in our 0.134 moles, divide that by the 0.250 liters, and that gives us a concentration of 0.536 moles per liter, or 0.536 molar. Other examples of this, maybe you don't have the right concentration units. You might not have liters, you might not have moles, but we can figure out both of those. So this example here now, we have a sample that has 200 milliliters, but we need liters, so we're going to have to turn milliliters into liters. It also gives us grams of this particular molecule when we need moles of a particular molecule. So we need moles, we've been given grams, but that's okay because we can convert grams into moles using our periodic table. So as long as we know the molecule we're working with, as long as we know the volume we're working with, we can figure these things out. So we can figure out what this weighs. So this has 2 carbons, each carbon weighs 12. This thing has 5 hydrogens, each hydrogen weighs 1. Has another hydrogen over here that weighs 1. It has an oxygen that weighs 16. So if we add all those up together, we get a mass of 46 grams per mole. So 1 mole of this molecule would weigh 46 grams. We don't have quite 46 grams, we only have 19. So 19 grams of this molecule divided by 46 grams per mole. The grams here cancel with the grams here. We're left with moles. And it turns out we have 0.41 moles of this molecule. Molarity is moles per liter, so we've got moles now up here. So we've got 1/2 of the thing we need to solve, but we need the volume. The volume we have so far is in milliliters, but we can turn milliliters into liters using the same formula we used on the other page. We know that there's 1,000 milliliters in 1 liter. Milliliters down here cancels with milliliters over here. We're left with 0.2 liters of sample. And then we just plug things in. 0.2 liters, that's our volume. 0.41 moles, that's our number of moles. Moles per liter. And the concentration, therefore, is 2.1 moles per liter, or 2.1 molar solution of C2H5OH. So that's our concentration of this particular solution in moles per liter. So one last example that we could do here to look at, figuring out molarity again. If you're given milliliters, you're going to have to turn it into liters. If you're given grams, you would probably have to turn it into moles. But as long as you do that, you can figure out the concentration. So this molecule here, C3HOH, we can figure out the number of moles that is, we can figure out the number of liters that is, and we can turn it into grams. So this molecule had 12 grams for the first carbon, 3 grams for the hydrogen, 16 grams for the oxygen, 1 gram for the hydrogen. That turns out to have a mass of 32 grams per mole. Grams here cancel with grams here. We have 0.295 moles of this molecule divided by 500 mils, or 0.5 liters. So we have 0.295 moles divided by half a liter. We have a concentration for this sample of 0.590 moles per liter. And then if we had a concentration, sometimes we could figure, if we had moles and liters, we could figure out how many moles per liter there are. If we have moles per liter, like we do here, here we have 0.8 moles per liter, and we have a volume in milliliters, so we can figure out how many moles there are. So we can use the backwards calculation and go and figure out how many moles we have, given that we already have a concentration and a volume. So we know that moles is per liter, so moles divided by volume gives you molarity. So we can rearrange that. So we're going to multiply the volume times the molarity. So molarity over here times the volume will give us the number of moles of the solute that is present. So then we just have to plug everything in. We got to convert it to liters, right? It's moles per liter, not moles per milliliter. So 15 milliliters is the same as 0.15 liters. And then we're going to multiply that 0.15 liters times the concentration of 0.8 moles per liter. In that case, liters here cancel with liters here, and we're left with moles, which is what we wanted to begin with. So we get the number of moles, and in this case, it's 0.012 moles of MgCl are in 15 milliliters of a 0.8 moles per liter solution.